lesson 2 of systems. It's on page 621 in your workbooks. I'm going to skip the exploration for the interest of time and go straight to the next page on 622, which is determining the number of solutions in a system of equations. So here's an example where they're asking us to determine the solution or the number of solutions. In the last lesson, we only ever saw one intersection point. So what are they referring to here? If we have a graph that is y equals x plus 5, I can graph that or sketch it approximately because I know that the slope is about 1 and the y-intercept about 5, so it's going to look maybe something like this. If I have my second graph, negative x plus 1, I know that the y-intercept is around negative 1 over here, and the slope is negative 1. So I can graph that here. If you graph this on a graphing calculator or on Desmos, you will see that there's going to be two intersecting lines. So we can say that there is one intersection or one solution. In this case, they're not asking us what the solution is. They just want to know how many. In part B, they said you have a line with an intersect of negative 8. So here's negative 8 down here. And it's got a pretty steep slope, a slope of 2. So I'll just draw approximately like this. And then in the second one, we have an intersection of 6, so it hits the y-axis here, and it has the exact same slope, quite a steep slope of 2. So these lines are actually parallel. Parallel lines are never going to intersect. So if they never intersect, then there's no solution. They're never going to touch each other. So the number of solutions in this case is 0. There are no solutions in parallel lines. In the last example, it is difficult to see what the slope is because this particular equation is not in slope-intercept form. So I'm just going to rearrange it. Negative 2y is equal to negative 6x plus 4. And then I'll divide everything by negative 2. So 3x minus 2. So now I can see that this one, wait a second, is the exact same equation as that one, just in a different format. So if I were to plot this equation, 3x minus 2 intersects at negative 2. It's got quite a steep slope, slope of 3. So there's the red line. And the green line would lie directly on top of it because it is the same line. If you were to ask me how many points of these two lines are intersecting, I would say all of them because all the red points are touching all the green points. So not only are we having one point of intersection, we have an infinite number of intersection points. So there are an infinite number of solutions because every single point touches every single other point. This is the same line. So the number of solutions can be 1, 0, or infinite. You can probably not think of a way to get two lines to intersect in only two places. You can do that with other shapes, but not with straight lines. So in general, if the lines intersect at one point, like so, then we would say that the number of solutions is 1. If the lines are parallel, like this, we would say that there are 0 solutions. So if there is one solution, you would say that the slopes are different and the intercepts can be anything. As long as the slopes are different, they're going to intersect at some point. Maybe the intersection point runs off the page. So for example, you could have two lines that don't look like they intersect, like so, but you know that if you were to extend the grid, eventually they will intersect somewhere. So long as the slopes are different, they are going to intersect somewhere. The intercepts don't matter. So any intercepts, and they're talking about y-intercepts, doesn't matter. If the slopes are equal and the intercepts are different, then we have parallel lines and we have 0 solutions. They never touch each other. If you have equal slopes and the same intercept right here, then it is the same line. Same slope, same y-intercept. The lines are coincident. That means they are the same. Can we determine the number of solutions a system has without graphing. Yes, you can. You just have to look at the slopes and the intercepts. But in order to look at the slopes, you cannot leave an equation like this. You need to convert it into slope-intercept form like this one. So if we convert that one to slope-intercept form, we're going to move the 3x over to the other side. So minus 3x from both sides. Then we divide everything by 5. So you can see that here is the equation in slope-intercept form. There's the green one. That one's already in the slope-intercept form. And you can see that they have the same slope, but different intercepts. This one has an intercept of 0. So that means that the lines are parallel, and there will be 0 solutions in this case. We can do the same thing to the second one. So we can move everything over. So we have 4y is equal to x plus 8. And then we can divide everything by 4 to try and get it into slope-intercept form. And let's take a look at this one compared with this equation that is already in slope-intercept form. And they are the exact same line. So they would lie on top of each other, and they would have an infinite number of solutions. And in the last example, we have to rearrange both the equations. So I'll just move that 7x over to the other side, 7x plus 12. And then in this equation, we have 6y is equal to x minus 5, divide by 6. And we can quickly see that they don't have the same slope, the blue and the red line. They don't have the same intercept either. So you can already tell that this is going to have one solution.